Good afternoon, everyone. Today, I'll be presenting on energy efficient boiler systems, a key to sustainable industry. My name is Shihab, and I am a can be improved to make industrial systems more sustainable. So, boilers are a crucial part of industrial operations, but they are also one of the largest energy consumers. That's why understanding how to optimize their performance can lead to both economic and environmental benefits. So, in today's session, we'll start with some background on industrial systems and their role in energy use. Then we'll move into the fundamentals of boilers, including their types, classifications, and efficiencies. After that, we'll discuss methods of efficiency estimations and highlight recommended actions. Finally, we'll share a case study and conclude with key takeaways. So before we jump into the discussion on boilers, let's look at what we mean when we talk about industrial systems. So industrial systems are the backbone of industrial facilities. They are the common systems you will find in almost every plant, and they are the main focus when we look for energy efficiencies. So some key systems are like boilers. Uh, Boilers are used to generate heat either for comfort or industrial use. Then there are HVAC systems, which are used for heating, ventilation, and air conditioning, and which maintains comfort and safe working environment. So lightings are another industrial systems. Lightings are not just lamps or fixtures, but they are also the controllers like the ballast, motion sensor, and the timers. Motors are the workhorses of industry, powering equipment and processes. Large facilities have hundreds or even thousands of them. Fans are used for ventilation, cooling, and air control. So compressed air is the common utility in many industries used to power tools and processes. Building envelopes are the walls, windows, doors, and roofs that separate the indoors from the outdoors. For this building envelope is critical for maintaining climate control. Steams are generated by boilers and widely used for heating process and even power generation. Together, these systems account for most of the energy used in an industrial facility. So today, we will mainly focus on boilers, but we will also touch on steam systems since they are often found together. So we will begin by looking at the fundamentals. What is a boiler? What are the main components of a boiler system? These things are key to understand how boilers operate and how their efficiency can be improved. So simply put, a boiler is a closed vessel that converts fuel into heat. But in reality, boilers are far more complex than that. They come in very many varieties, depending mostly on the fuel they use and the application they serve. Boilers can run on natural gas, propane, biogas, coal, or even electricity. The heat produced by a boiler can be used in many different ways. It can heat water to provide hot water or steam for a facility. It can heat transfer fluids like propylene or ethylene glycol for snow melt systems, freeze protections, or process heat. And it can heat air for space heating or industrial process. Because of these different uses, boiler designs can vary widely. Still, most boilers share several key components, which we will look at the next slide. So if we look at the key components, we can see at the heart of every boiler is the combustion chamber, where the fuel is burned. In gas-fired and oil-fired boilers, you will also find burners that deliver the fuel into the chambers, regulate the proper fuel to air mixtures for complete combustion. The heat produced then passes through a heat exchanger where it's transferred to water, which produces hot water or steam, and to a heat transfer fluid depending on the application. The exhaust gases are carried out through the flue gas system, while a control system, especially in modern boilers, keep everything safety and efficiently. Of course, there are variations. Electric boilers don't have a combustion chamber or burners, and biomass boilers may not use burners either. But no matter the design, each component plays a critical role in ensuring boiler runs smoothly and sustainably. Now that we understand the basic of boilers and how they work, let's get into the different types of boiler systems. As mentioned earlier, boilers aren't one size all, so they come in various design depending on the applications, like fuel source, capacity needs. So let's look at some of the ways that boilers can be classified and application of each type. Boilers can be classified by the type of fuel they accept, the internal design, their application, or their air movement. There may be other classifications methods, but these are four of the main design concepts considerations. So the first one is fuel type. There are different fuel type boilers, like gas-fired boilers that runs on natural gas, propane, biogas, or hydrogen. They are most common because the natural gas is cheap and it is widely used in the USA. So most of these boilers can be converted to use different types of gas and only small design changes. Oil fired boilers burn fuels like diesel, kerosene. Since the fuel or has to be delivered by truck, they are less common and easily found places where there is not availability of natural gas. Coal-fired boilers are used less often today, but still exist in some industries. Coal usually has to be transported in, and strict emission rules often require expensive pollution controls. Next one is the biomass boilers that burn organic materials such as wood chips, crop waste, or even algae. They are uncommon but work well for facilities that already generate a lot of organic waste. Electric boilers don't use combustion. Instead, they rely on electricity to produce heat. So they don't create direct emission. They're clean but less commonly used in the industries, since electricity usually costs more than other sources of gas, other energy sources. So next classification is internal design. With most boilers, if you would open the outer shell, you'll find a series of tubes. Boiler can be classified by what is inside these tubes. The differences between these two are best depicted visually. So the image on the left represents a fire tube boiler. In these boilers, tube carry the heat generated by the combustion of the fuel. This tube passes through the water-filled boiler vessel and transfers heat into the water. This type you will mostly find in the facilities for heating or small industrial processes. The image on the right represents a water tube boiler. In this case, the tubes are carrying water through the hot furnace environment where the heat is transferred into the water. These boilers are more complex and generate higher pressure, so they are better for large industrial applications. There are also hybrid designs that utilize both of these concepts. Next boilers are based on application. So there are different boilers like hot water boilers. These provide hot water for restroom, kitchen, so mostly used in the houses. Then the steam boilers that heats water to the boiling point to make pressurized steam. Steam is widely used in industry for heating, drying, sterilizing. Then the thermal oil boilers, this heat specific oil that carries heat through the facility. Unlike steam, thermal oil works at low pressure, can reach higher temperature, and doesn't freeze. And it is not corrosive. That makes it a good choice in some cases, though steam can be more efficient where latent heat is an advantage. Boilers can also be classified by how air is supplied for combustion. Natural draft boilers use chimney height and temperature differences to move air. Since airflow isn't controlled, the air-fuel ratio is inefficient. Forced draft boiler use a fan at their inlet to push air into the combustion chamber. The fan speed controls airflow, which allows precise airflow ratio, and it has better efficiency. Induced draft boilers use a fan at the outlet to pull air through the system and exhaust flue gases. They are not at precise for air fuel control but help prevent flue gas leaks. Balanced draft boilers combine both a fan at the inlet and another at the outlet. This keeps furnace pressure stable, making them most suitable for large utility scale power plants. So for this presentation, we will mainly focus on natural gas boilers and steam systems as they are the most common use. Now that we have discussed the basics of boiler system, let's keep a deeper dive into boiler efficiency. So efficiency represented by the Greek eta is simply the proportion of energy input successfully turned into useful output. So let's take a simple large natural gas boiler for a steam system. For example, let's assume that a boiler has 1 million BTU uses input of 1 million BTU per hour. So that means the boiler will use 1 million BTU worth of natural gas. So we usually pay natural gas by MCF. So that means it is about 1 MCF. And let's say the boiler has 80% efficiency. That means the boiler will give us an output of 800,000 BTU equivalent of power. So that means that in this case, the remaining 20% of the energy is lost. These losses can occur for various reasons, including thermal loss from the surface of the burner or incomplete combustion of fuel. So we'll discuss all these losses shortly. So here so why do these losses occur? So the biggest energy loss in a boiler comes from hot flue gases, which carry away unused heat. Usually it's about 20% of the fuel energy. So other losses are like radiation and convection, which amounts for 1 to 4% of the fuel efficiency. Another one is blowdown losses. It's up to 3%. So it is for the releasing of hot water to control impurities. Altogether, these losses added up to 20 to 30%. That means most boiler has efficiency around 70 to 80%. And when you include the steam distribution system, you can add another 5 to 15% along the way. So how we determine the boiler efficiency? There are several approaches. The general represent a trade-off between complexity and accuracy. We can use product specification, software application, calculation of losses, or direct measurement. Let's discuss each of these in more details. So the easiest method of estimating the efficiency of a boiler is to look at the product specification or equipment level. The input and output is in BTU per hour are provided, allowing the efficiency to be calculated easily. In this case, the boiler has 84% efficiency. So the nice thing about this method is that it is very easy. There are no tools require just a simple calculation. However, this is the rating when new and operated under ideal condition. When the boiler is operated under ideal condition, it doesn't consider wear and tear losses, potential changes due to repair or maintenance, improper setup. In other words, this is the highest efficiency the boiler could have, not the efficiency it is currently operating. This method also not work if the manual wasn't kept and the label is removed or on. So the next way to calculate efficiency is to use software application. So the US Department of Energy maintains a free software that is called Measure, which is designed to help industrial facilities manage their energy use and improve energy efficiency. One tool within Measure is a stack loss calculator tool. This tool will calculate the stack loss, which, if you recall, is the primary source of loss in the boiler. This is going to provide a more accurate efficiency measurement than the equipment level will provide. However, the software requires the stack gas temperature, ambient air temperature, and either the excess air or the oxygen in the flue gas to calculate the efficiency, which will have to be measured directly. So the best way to measure boiler efficiency is a combustion analyzer. Its probe is placed in the exhaust stack to measure temperature, oxygen levels, and other properties. These readings are then entered into a stack loss calculator to estimate efficiency. This method is more accurate but comes with a cost. A basic analyzer starts around 500 with high accuracy models with calibration certificate can cost $5,000 or more. It is worth noting that this method doesn't account for all losses. Radiation, convection, and blowdown loss can add around 2 to 7% efficiency loss. So if we want to take a step further, we can include the other losses. Using the combustion analyzer to measure stack loss was already discussed. That leaves the surface loss, blowdown loss, and the bottom ash loss. Blowdown loss can be determined by measuring the temperature of the blowdown water and the temperature of the feed water, as well as the volume of blowdown water released over a measured period of time. Surface loss can be estimated based on the surface temperature and the surface area of the boiler. Bottom ash loss is only an issue when burning coal or other organic material, but quantifying the loss requires determination of the amount of bottom ash, carbon content of the bottom ash, and the temperature. So in addition to the combustion analyzer, this will also require tools like infrared temperature guns to measure surface temperature and thermocouple thermometers to or similar kind of things to measure water temperature. Surface area of the boiler would need to be measured or estimated. These additional tools are relatively inexpensive and are not difficult to use, but the calculations required to accurately estimate these losses are more complex. Next, finally, the most accurate but most complex method is the direct measurement of input and output. To measure the input, we need to know how much energy is contained in the fuel that the boiler uses, the amount of fuel used per hour, and the gross calorific value, which is how much energy the fuel contains per volume, must be known. The gross caloric value of different fuel is easy to find, but accurately measuring the quality of the fuel used can be challenging. To measure the output, we need to calculate how much steam is generated and how much heat that steam gained from what is it has fed into the boiler as water. Another way to estimate boiler efficiency is through direct measurement. So this approach uses multiple flow meter and thermometer to measure both the energy going into the system and the energy coming out. The big advantage is the accuracy. It's the most precise method we have. However, it comes with challenges. It requires sophisticated equipment careful installation and ongoing monitoring, which make it more complex option compared to other methods. Now that we have identified where efficiency losses and discussed some factors influencing efficiency, let's begin exploring how we can improve the efficiency of the system. These following recommendations aim to improve boiler efficiency, lower energy cost, and reduce emission. We'll walk through actionable strategies designed to address the losses we have seen and help make your system more sustainable and effective. Let's start off with our first recommendation, optimizing the air to fuel ratio. So this is one of the most critical steps in improving boiler efficiency. Getting the air to fuel ratio right is essential. Too much air result in excess heat being lost up the stack, while too little air causes incomplete combustion, which is also a which also cost us efficiency. Both conditions are not only waste energy but also drive up operational costs. So by fine tuning this ratio, we can ensure that more complete combustion, better heat transfer, and improve fuel savings. So the measurement from a combustion analyzer along with software like measure can be used to determine air to fuel ratio and calculate potential energy and cost savings from making adjustable to the boilers. After measuring the ambient temperature, combustion air temperature, stack temperature, excess air and emission using the combustion analyzer, measures flue gas tool can be used to determine the amount of excess air. After collecting combustion data in the field, the next step is to put the data in the measured flue gas tool loss. By inputting the data collected from the combustion analyzer into the software along with some other basic information, including fuel cost and operating hours, the software can estimate the losses in the flue gas and excess air. Additionally, based on the details provided, the software can also estimate fuel use saving and corresponding cost saving due to the modification. Next, we will discuss using economizer to improve efficiency. An economizer is a device that recovers wasted heat from a boiler exhaust stack. This recovered heat can preheat the water entering the boiler, which improves the efficiency and saves energy. The device captures both sensible heat related to the temperature change and latent heat. For a boiler with an input of 1 MMBTU per hour, about 15% of that heat is normally lost. By recovering just 20% of that heat lost, we can save around 30,000 BTU per hour. This could lead to an annual saving of $2,600 at a natural gas cost of $10 per MMBTU, with a payback period of around 2 to 3 years. Next, we will discuss the replacement of old burners with new, more efficient burners. Old burners are often inefficient and inaccurate in how they mix fuel and air. Over time, this leads to incomplete combustion, higher emissions, and waste of energy. So the table shows the finding of a case study at a facility with a larger 50,000 pound per hour process boiler. The boiler was found to use about 500,000 MMBTU of natural gas per year that was costing $4 million. By replacing the old burner with a burner that improved energy efficiency by 2%, a saving of over 12,000 MMBTU and nearly $100,000 per hour. At an installation cost of $75,000, the simple payback period is less than 1 year. Next recommendation is to insulate hot surface and boiler pipes. According to US Department of Energy, proper insulation can reduce those losses by up to 90%. So any surface above 120 degree Fahrenheit, including boiler surface, piping and fitting should be insulated. So it's one of the simplest yet most cost-effective efficiency upgrades available. You will see from the table that even uninsulated low pressure steam lines can have significant waste. For instance, just 100 feet of uninsulated 2-inch steam line can result in a loss of 235 MMBTU of energy per year. At a cost of $10 per MMBTU, that can represent a waste of $2,350 per year, which the situation could be corrected for less than $250 in materials. The slide shows some common insulation materials for steam pipes, like calcium silicate is mostly used due to its durability and thermal performance. So, one often forgotten part of a steam system that can affect efficiency if not properly maintained is steam traps. Steam traps play a critical role in efficient steam system operation. Here, you can see a schematic diagram of a typical steam system with traps located throughout the to remove condensated without losing valuable steam. To keep these systems running efficiently, it is important to regularly inspect traps for leaks or malfunctions. Next, we will talk about identifying and repairing steam leaks. So what you see here are example of typical steam leaks, often found around joints, valves, flanks, and corroded section of pipes. This might look minor, but they can waste a significant amount of energy and water over time. While steam leaks are often visible and audible, some may not be immediately apparent. The pipes may be close to the ceiling or otherwise not easily visible, and a noisy environment may mask the sound. So, an ultrasonic leak detector can be used to help locate these leaks by detecting ultrasonic noise associated with the pressurized leak. They are very simple to use and are really affordable. Finally, we will discuss overall boiler system maintenance. To keep a boiler running, we should have dedicated operator, do daily checks like manual blowdown, check burner heads regularly, use automatic systems to save work, monitor chemical dosing monthly, schedule 2 to 3 shutdowns a year for cleaning, use modulating controls to keep steam pressurized, and these steps will ensure the boiler is safe, efficient, and last a longer time. So here are the references we have used. Thank you for your time and attention. So we have seen how boilers play a vital role in industry, how efficiency can be measured, and the actions we can take to improve the performance. Together, these strategies can save energy reduction cost, uh, can save energy, reduce cost, and support sustainability. So here is the QR code. I would greatly appreciate your feedback. Thank you.